Thanks. So thank you for the organizers for this opportunity and all of you for being here after lunch. What I'll talk about today is an approximate version of a very classical result in convex geometry. It's almost a 100-year-old theorem by Caratheodory, and the emphasis of the talk will be on algorithmic applications of this approximate version. I'll show how this sort of new approximate version leads to very novel sort of algorithmic ideas, very novel algorithms, for some sort of very sort of natural and well-studied problems. So let me start by recalling the classic. So as I said, Caratheodory's theorem, fundamental result in convex geometry, used to prove very essential basic facts like extreme optimal solutions of linear programs are basic, so on and so forth. And what the theorem says is that if any vector in the convex hull can be expressed as a convex combination of at most d plus 1 vi's. So what do I mean? Say you're given vectors v1 through vn. So all these vectors are d-dimensional. So my ambient space is d, and I'm now looking at a set of vectors. Then every vector w in the convex hull, it does not matter how many vi's I give you. Give me any vector w which is in the convex hull of these vi's. I can always express this vector w as a convex combination of some d plus 1 vi's. So if your ambient dimension d, these vectors are say 100 dimensional, and you have 1 million of these vi's, still give me any vector w in the convex hull, I'll only need 100 plus 1, the ambient dimension plus 1 vi's to express w as a convex combination. So a very informal way of saying is that if you're lost in d dimensions, then you need d plus 1 satellites to exactly triangulate your position. On a plane, it's exactly 3, and hence the word triangulation. Right, and this bound is tight. It's not too difficult to come up with vi's and a particular w such that to express w exactly, you do need d plus 1 vi's. Any smaller and you cannot express w as an exact convex combination. So simple examples, leave it as an exercise for you. But let's now consider a very natural approximate version of this theorem. And to do that, let's pick a norm, any norm p greater than or equal to 2. So just a reminder, I'm working in d-dimensional space. My ambient dimension is d. I have a whole bunch of vectors vi's, and I'm now picking any norm, any p norm which is beyond the Euclidean norm. So any p greater than or equal to 2. Now what one can show is that for every vector w in the convex hull, there's in fact an epsilon closed vector, epsilon closed in this p norm, such that this w prime requires only 4p over epsilon square vi's to be expressed as a convex combination. So there's some scaling going on, and I'll explicitly mention it in the next slide, but just to sort of emphasize the point, what I'm saying is that it doesn't matter where w is, and w might require d plus 1 vi's to be expressed as a convex combination, but doesn't matter where w is, there always exists an epsilon closed vector, w prime, epsilon closed in your norm of choice, such that this nearby vector can be expressed as a convex combination of these many vi's, 4p over epsilon square. So what's notable about this result, what's striking here, is that it's dimension free. The ambient dimension d does not make an appearance here. So as I said, there's some scaling going on, so let me bring up the formal theorem statement. And the formal theorem statement is that I'm given a set of vectors v, they lie on or inside the p unit ball. So I have some ambient dimension d, some norm of choice p, which is more than 2, and all these vectors have p norm at most 1. So they lie all on or inside the p unit ball. And what the theorem says is that for every vector w in the convex hull, is guaranteed to exist an epsilon closed vector in this p norm, such that this nearby vector can be expressed as a convex combination of only 4p over epsilon square vi's. And again, the striking feature of this theorem statement is that the ambient dimension D does not make an appearance. It's dimension free. So if you want one single tool, one single takeaway from my talk, this is it. That's the theorem. If you understand this, sort of, yeah, I'm kind of done. What I'll do is, instead of like proving this result, I'll kind of emphasize some interesting algorithmic applications that come out of this. In particular, I'll talk about how to find approximate Nash equilibria using this theorem statement, and in general, how to solve approximately solve sparse quadratic programs. So, but before moving on to the application, let me say a few words about the proof of this theorem. So one way to establish this is by instantiating this heavy hammer from Banach space theory called Maury's lemma. Alternatively, I have a proof via Khinchin's inequality. And if time permits, I'll give you a proof sketch that uses Khinchin's inequality. But as I say, for the thrust of the talk will be on how do we use this dimension-free result to get interesting algorithms. So that's the line, that's the main theorem I want to talk about. If there are questions, I can address them, or I'll sort of move on to some algorithms. Yes. Okay, that's a good question. The idea is, the important aspect is that I have it for arbitrary norms. For the Euclidean norm, it's which is sort of the more popular, like perceptron or boosting, it's sort of much, much simpler. I have this result for arbitrary norms, and I have this dependence on the norm here. I will critically require this result to hold for arbitrary norm. Yeah, not by arbitrary norm, I mean for general P's. Yeah, it's not an atomic norm or anything. So, I mean, it doesn't hold. Like for P equals to 1, it will not hold. So even if you look at the standard L1 ball, right, the result will, I mean, you will not get a dimension-free result. So, I mean, again, simple example would show you that if you are working with the L1 norm, you cannot hope to get a dimension-free bound. Again, for vector norms, for P less than 1, this thing kind of degrades very fast. So, yes, right. Yes, and it's being used here. And it goes into it follows from Khinchin or from Maury. So it's like a type, cotype constants of the underlying Banach space. But without getting into that, when I say arbitrary, I'm just being loose here. All I mean is I have it for not just for P equal to 2 or P equal to infinity. I want this to hold for general P, vector P, LP norms. So I'll instantiate this result. You'll see it when I talk about the application, that I'll actually instantiate for P as log n. So and the question was why, like how does it compare to boosting? Boosting is a very special case where P equals 2. And that's much easier to establish. You don't need any of these things. It's a half a paragraph exercise. Yeah, so for example, the Birkhoff von Neumann polytope, for that you can actually do better. You can get something that's like 1 over epsilon. But those are like tailor-made arguments for that. So there are known cases where you can actually do this, like improve upon this bound, but in general, this is tight again. There are cases where for P greater than or equal to 2, you do need, modulo this constant 4, you do need P over epsilon square VIs for any vector in the epsilon ball of W. So there exists a set of vectors VI, particular norm, and a particular W, so that any epsilon closed vector requires order P over epsilon square VI. But yeah, for special, like for Birkhoff von Neumann, in particular, you can sort of improve upon this. 1 over epsilon square over, but there's no sort of, I think it's 1 over epsilon. I can work this out after the talk, offline. Yes. you have to like, okay, so there's a recent result by Mirokni et al. That show that this does work with online mirror descent, not Frank-Wolf. But yeah, you have to sort of analyze it. And again, the catch being that I'm working throughout with the P norm. So if you were to do this, that these lie in the 2-unit ball and then you apply Frank-Wolf, then you probably would get such a bound. The relevant aspect is the entire theorem is with respect to one single norm. So even this is a subtle point, but it is notable that even the scaling I'm assuming here for these VIs is the P norm, not the 2 norm. Yes, so I mean, you can be, for purposes of talk, I'm writing it this way, you can write this as 4 max P or log D. You don't have to sort of go beyond the log Dth norm. Again, just for ease of presentation, I'm writing it in this form. You really don't have to push it to that. And again, in the infinity norm, you can actually assume that these VIs have infinity norm at most points. So they are on or inside the hypercube. What is that? Doesn't hold. Like you can have this to be arbitrarily bad. So formally, the result for P less than between 1 and 2 is that you have order 1 over epsilon to the Q, where Q is the Holder conjugate of P. So but for one norm, the Holder conjugate is infinity, that bound is moot. I mean, for one norm, the best you can do is sort of D. You can't really escape. You can't hope for examples are quite simple, like simplex and so on. You can show that this is sort of required. Everything except 4 is tight. Okay, so that's the theorem statement, and with this dimension-free bound, I'll try to move on to applications. And the first application that I'd like to talk about is the central problem in algorithmic game theory, which is that of computing equilibria, computing Nash equilibria. So this problem actually lies at the core of the intersection of computer science and game theory. And the algorithmic question is as follows. I'm given payoffs of players. I'll formally define what I mean by equilibria and what this computational problem is, but let me just give a high-level description first. The problem is that I'm given the payoffs of the players. So I have a game, I'm given these payoffs, say I have 2 players, so I'm given these 2 payoff matrices, and the question is, or the goal is to design algorithms, hopefully efficient algorithms, that find underlying Nash equilibria of these games. So Nash's celebrated result says that for such finite games, there always will be a Nash equilibria, so existence is guaranteed. The question that sort of broadly motivates us is, are there efficient algorithms for finding these Nash equilibria? And just to recall, these equilibria actually represent stable outcomes of games, of strategic interactions. These are distributions where players don't have an incentive to unilaterally deviate. I'll formalize all of this. All I want to say is that the overarching question I'm looking at is, given a game, given the payoffs of players, are there efficient algorithms that find underlying Nash equilibria, underlying stable outcomes of these games, of these strategic interactions? And both on the algorithm and the complexity side, there's been a lot of work addressing this question. There's a long line of work that sort of culminates in this popular result of Chen, Deng, and Teng, shows that it's unlikely that, in fact, there are efficient algorithms for finding Nash equilibria. In fact, it's unlikely even in the case of 2-player games. So the most fundamental model of strategic interactions, you have just 2 players, 2 strategic agents. Even then, finding a Nash equilibria is a computationally hard problem. That is, it's unlikely that there exists polynomial time algorithms that, given these payoffs, can find these distributions efficiently, can find these Nash equilibria efficiently. So, this hardness result in mind, a natural sort of question, a natural way to proceed for a computer scientist is to in fact consider, instead of exact Nash equilibria, approximate Nash equilibria. That is, these are distributions where no player has an more than say an epsilon incentive to unilaterally deviate. So they're approximately stable in that sense. Again, I'll give you formal definitions in a few slides. But now the question is, okay, can we find approximate Nash equilibria efficiently? So again, there's a recent hardness result by A.V.R. Rubinstein that shows that even in this case, a polynomial time algorithm is unlikely. There's a quasi-polynomial time hardness result under ETH. So again, it's unlikely that there is an efficient algorithm, even if you are not even if you're looking for an approximate Nash equilibria, not an exact one. This turns out to be tight, and I'll mention this popular result of Lipton, Markakis, and Mehta that actually gives you a quasi-polynomial time algorithm for finding approximate Nash equilibria. Again, this is sort of informal, I'll make it formal soon, but these are sort of the heavy negative results that sort of motivate us to consider games with structure. So the focus of the question, the focus of our work is, can you do this? Can you find efficient algorithms if your underlying game is structured? And I'll formally define what I mean by this, but the punchline is that, yeah, if you have structured games in a formal sense, then you can, in fact, compute approximate Nash equilibria efficiently. And in fact, the result will sort of interpolate beautifully between like structured games and this general quasi-polynomial time algorithm. So that's sort of the broad agenda for the next few slides. And in particular, I'll use the approximate Caratheodorys theorem to solve this problem, to address finding approximate Nash equilibria. Okay, so it will be a bit more specific about things. So just to recall, I'm sure most of us know this, that two-player games essentially model settings where two self-interested entities, two agents, two players, simultaneously select an action to maximize their own payoff. So classical examples include rock, paper, scissors, or prisoner's dilemma, and so on. So there are two players, each of them say have n actions each of them picks an action, and the goal for both the player is to pick an action that maximizes her payoff. A bit more formally, what I'll do is use matrices A and B to denote the payoffs of the two players. So I have two players, both players say have n actions each. The actions of the first player index the rows of these two matrices. The actions of the second player, say the column player, indices the columns of these two matrices, and the first matrix represents the payoff of the first player, the second matrix represents the payoff of the second player, by which I mean that if the first player plays action I, row I, and the second player plays action J, row J, the payoff of the first player will be Aij, and the payoff of the second player will be Bij. So this is just a tabular way to write down all the payoffs of the two players. So throughout, I'll use matrices A and B to denote the payoffs of the two players. So that's the formal setup. And as I mentioned before, equilibria represent probability distributions. They represent probability distributions via which the players pick an action. So throughout, I'll use X to denote the probability with which, the probability distribution via which the first player picks an action. So X is a distribution on the rows, the number of the actions of the first player, and Y is a distribution of the columns of these two matrices. So the second player plays an action, picks a column based on distribution Y. So these are n cross n matrices, and hence these are probability vectors over 1 through n. A standard notation, very basic in game theory, the most fundamental model of a game, two-player bimatrix games. Okay, so with this notation in hand, the definition of Nash equilibria is sort of quite intuitive. It denotes a pair of probability distributions, X and Y, one for the row player, the second for the column player, such that in expectation, neither of the two players can benefit by unilaterally deviating. What do I mean? So this term on the right here represents the expected payoff of the first player. know that A is the payoff matrix of the first player. So this X transpose AY is just a term by term product which says that if the first player picks its action, picks one of the rows based on distribution X, and the second player picks one of its actions, i.e. one of the columns based on distribution Y, and this is the expected payoff of the first player. Analogously, this term here on the right, X transpose BY, is the expected payoff of the second player, B being the payoff matrix of the second player. And what these inequalities say is that if the second player, say, continues to follow distribution Y, sticks to playing based on distribution Y, then the first player cannot benefit by switching to any single action I. So if the first player says, oh, let me play row I, let me play action I, its expected payoff is going to be this. EI is the standard basis vector. And this inequality says that in expectation, the first player cannot benefit by this unilateral deviation. And analogously, if the first player continues to play X, the second player cannot benefit by unilaterally deviating to any column or any single action J. So that's the definition of a Nash equilibria. And the computational problem we are interested in is the following. I'm given two n cross n matrices, A and B. I want to find two distributions, X and Y, that satisfy these two n inequalities. And the hardness result I mentioned was that it's unlikely that there exists a polytime algorithm for this. It's unlikely that I give you two matrices, X and Y, you can find two distributions that satisfy these inequalities. Those such distributions are always guaranteed to exist. That's Nash's theorem. So there always will be such distributions. Finding them is computationally hard. And so along these lines, the definition of an approximate Nash is that neither of the two players can benefit by more than epsilon by unilateral deviation. So if the first player deviates unilaterally, the second player continues to play according to distribution Y, then the payoff of the first player cannot go up by more than epsilon. So epsilon, it's an additive guarantee. It's an additive requirement. And that's any distribution X and Y that satisfy these 2n inequalities is said to be an approximate Nash. A, Y, yes. Yes? Of the columns of A. A is a matrix. Yes, it is. Yes. Yes. So it's called the best response condition. It means that X is completely supported on the largest coordinates of A. Yes, it's an equivalent definition of Nash equilibrium. Exactly. It's called the best response. Yeah. Both, yeah, I mean, it's not intuitive. It's an equilibria. You're playing something, I'm best responding to it. At the same time, I'm playing something and you are best responding to it. Hence, neither of us can benefit by unilateral deviation. I mean, that's sort of the intuitive idea, but exactly the conditions. It's a less than equal to. I cannot have a strict inequality. But yeah, that's another definition of Nash equilibrium. Anything else? Okay, so that's the definition of an approximate Nash. And again, the computational problem is I'm given two matrices A and B, want to find two distributions X and Y that satisfy these inequalities, one, some fixed parameter epsilon. Again, the quasi-polynomial time result says that there is a quasi-polynomial time algorithm for finding such distribution, and under ETH, that's the best one can hope for. Okay, so with these definitions in mind, let me kind of get to some history about equilibrium computation. There's a long line of work. It's a very well studied area, starting from this sort of classical result of Lemke-Hausen that gives an exponential time algorithm for finding exact Nash equilibria. It's a simplex-like method that sort of walks on the polytope. And again, in light of the hardness result I mentioned, it's not surprising that this is sort of an exponential time algorithm. there are special classes of games though where much better results can be obtained. In particular, there are special structured classes of games where polynomial time algorithms exist for finding exact Nash equilibria. Sort of the most popular class is these so-called zero-sum games. These games model strict competition. These are games where the sum of the two payoff matrices is all zeros. So entry by entry, if I sum up the payoff matrix A of the first player and the payoff matrix B of the second player, I get the all zeros matrix. Hence these games represent settings wherein whatever the first player loses is exactly equal to what the second player wins and vice versa. Classical set of games, and these old results by von Neumann and Danzig show that via linear programming duality, you can find exact Nash equilibria for zero-sum games in polynomial time. So, not really, but the min-max and Danzig and yada yada yada. And they didn't write it as a polytime algorithm for it. They just gave this LP formulation for it. In fact, like von Neumann only gave the min-maxes. Like the connection to duality even came much later. But yeah, I mean, once you have that, you just it's an LP then. Yeah, so, but this is all I'm saying. Yeah, LP duality sort of kicks in here, and using that we can find a polytime. There are other sort of interesting classes of games. Here's this result by Ruta, Jugal, Atsul, and Milinsohni, which says that if your game is a rank 1, that is, you look at the sum of the two payoff matrices, A and B, and that sum matrix, A plus B, is of rank 1, then again you can find an exact Nash equilibria in polynomial time. So again, another interesting class of games which admits efficient computation of Nash equilibria. And along these lines, there have been a bunch of work in the computation side of approximate Nash equilibria as well. There's sort of a popular result by Lipton, Markakis, and Mehta that does a very simple support enumeration and shows how to find an approximate Nash equilibria in time n to the log n over epsilon square. This is a quasi-polynomial time algorithm. It finds an epsilon Nash equilibria. Again, there are specific classes of games wherein you can find an epsilon Nash efficiently. This is a very nice work by Nogailon and others that shows that if your rank of the game is small, again, rank means that the rank of the sum of the two payoff matrices is small, then you can find an epsilon Nash very efficiently. And this sort of result goes by this nice covering argument over subspace and these sort of epsilon net type results. It's very nice results in and of itself. But again, if your game is structured in the sense that it has low rank, the sum of the two payoff matrices is of low rank, you are good. Then you can again find an epsilon Nash efficiently. Some other like poly terms I'm ignoring here, just again ease of presentation. So the result I'll talk now is sort of contributes to this line of work and looks at a very natural complexity measure of games, looks at a very natural measure, the sparsity of the game. I'll formally define what I mean by sparsity. The result says that if the game is sparse, it's near zero sum, then again you can find an approximate Nash equilibria efficiently, and at the other end of the spectrum, you can also get the general quasi-polynomial time bound of, recover the quasi-polynomial time bound of Lipton et al. So that's the sort of measure I'll use to sort of define structure or measure structure over games. In particular, I define the sparsity of the game to be the number of non-zero entries in any column of the sum of the two payoffs. So recollect that A and B are the two payoff matrices of the game. They are the two payoff matrices of the two players. So what I do is I look at the sum of these two matrices, entry by entry sum, and I say that a game is S sparse if any column of this sum matrix has no more than S non-zero entries. Again, this is sort of a simplification. This result will hold if you have row sparsity or you have some affine combination that's sparse. Nonetheless, for the purposes of the talk, let me stick to this simple definition that a game is S-sparse if the sum matrix has at most S non-zero entries. Right, so that's the definition of sparsity, and just to sort of hammer it in, note that if I have a zero-sum game, so this sum A plus B is the all zeros matrix, then sparsity is zero. Every column is just all zeros. And in general, since these are n cross n matrices, the sparsity can be at most n. All the entries are non-zero, and hence I have an n-sparse game. So the sparsity measure ranges from 0 for a zero-sum game to n for a general game. That's how I'm kind of measuring the structure of the game. And note that it's a very natural class of games. It's saying that, okay, so you are in a setting where most of the time what one player loses is exactly what the second player wins, except you have some S exceptions. So modulo these S settings per column, most of the time the game is zero sum. It's a near competition, it's a near perfect competition. And what the result that follows from approximate Caratheodory is that if you have a two-player game which is S-sparse, then you can in fact find an epsilon Nash, you can find an approximate Nash in time n to the log S. That sparsity goes up in the exponent with a log. So that's the result for general S-sparse games. And again, as a standard, since I'm dealing with additive approximations, the payoffs are normalized between -1 and 1. And let me sort of mention the relevant implications that when S is a fixed constant, it's a small number, then you are close to a zero-sum game. And in that case, log S is a constant and you get a polynomial time algorithm for finding epsilon Nash. And in general, since S can be no more than n, in the extreme case, you recover this quasi-polynomial time result of Lipton. So it interpolates across the entire spectrum of games from near zero-sum games to general pi-matrix games. And so that's the single result. Okay, so that's the result I want to sort of give the more or less the proof sketch for. And the idea is I'll use Caratheodory, approximate version of Caratheodory's theorem to establish this running time bound. And just let me mention as an aside that S-sparse games are in fact hard. So if you want to find exact Nash, again, it's unlikely that there is a polynomial time algorithm. So it's the approximate Nash is the best one can hope for. Right, so on to some technical parts. So this is the definition of Nash Equilibria that I sort of mentioned some time ago. It's again a pair of distributions x and y that satisfy these 2n inequalities. No one has an incentive to deviate unilaterally. Now here's this sort of classical bilinear program that captures Nash Equilibria of the game. This is a program by, it's a bilinear program by Manxerian and Stone. So I don't really need for you to understand the nitty-gritty details of this bilinear program. All I want to say right now is that, believe me, there is a bilinear program such that the optimal solution of this bilinear program correspond to the Nash Equilibria of the game. That is, give me matrices A and B. If I am able to optimally solve this bilinear program, I'll have a Nash equilibrium. So the optimal solutions of this bilinear program are exactly the Nash equilibria of the game defined by matrices A and B. Again, sort of technical details that don't really matter for the purposes of the talk. All I want to sort of highlight here is that the only computationally non-trivial aspect of this bilinear program is this term in the objective. All the constraints are linear in the decision variables x, y, pi1 and pi2. It's a bilinear program where all the constraints are linear. X and y are distributions, these are two scalars, everything is linear here except for this term in the objective with this sum of the two payoff matrices showing as is. So that's the term that sort of makes this problem computationally hard. Like solving this bilinear program is not a polynomial time task. Note that this is exactly the matrix for which I had made the sparsity constraint. This is the sum of the two payoff matrices. In particular, if this is all zeros, this kind of term vanishes away and I get a LP. So this directly tells you why you can find Nash equilibria of zero-sum games in polynomial time. That's just a linear program. Here it is. But this is the matrix that I'll deal with, the sum of the two payoff matrices. That's C. I'll use C to denote the sum of the two payoff matrices, and this is the bilinear program I have. Again, another fact that I'll not really sort of prove, but which is true, is that if you find an approximate optimal, near optimal solution for this bilinear program, you'll get an approximate Nash equilibrium. So a feasible solution, which is epsilon close to the optimal, is a epsilon Nash equilibria. Again, another technical fact, not too hard to prove, but for purposes of talk, just take it as a sort of as a given. So the goal is solve this bilinear program or approximate this bilinear program. If you do that, you have the Nash equilibrium of the game. You have a Nash equilibrium of the game. Yes. Okay, this is all ones vector. This is component wise. All ones, yeah. Just think of them as some linear constraints. Won't matter for us. All right. So this is the bilinear program that we want to solve or approximate. And here's the sort of connection to cathode. Here's the light bulb. The point is that if I look at this matrix C, which is the sum of the two payoff matrices, and this vector Y, Y is in fact a probability distribution. It's a probability vector. So Cy is nothing but a convex combination. It's a weighted average of the columns of C, right? So here's a nice idea. Say X star Y star is a Nash equilibria of this game. I don't know what X star Y star is, otherwise I'd be done, but it's there, it exists. That's Nash's theorem. Now, say magically an oracle gives you this vector U star, which is C, the sum of the two payoff matrices, times this Y star, the probability distribution of the second player in the Nash equilibria. So if I give you this vector U star, then you are golden. Why is that? Well, then all you can do is simply write this linear program, replace Cy by U star, the vector that's given to you, and add this linear constraint. Simple idea, once you know this vector, you are done. You have an LP, and solve this LP and sort of extract back the Nash equilibria. Of course, you don't know X star, Y star, and moreover, you don't know U star. Otherwise, we're all happy. Nonetheless, what's important to note is that, again, a technical fact, which is kind of intuitive, but I'll not prove it, is that a vector that's close to Cy star in fact suffices. If you don't know exactly U star, but I give you a vector that's epsilon close to it, again, you can go through the motions and show that an analogous LP would give you an approximate Nash equilibrium. So you don't really need to know this golden vector exactly. Something approximate would translate into an approximate Nash equilibria, again, by writing a analogous linear program. But that's the idea. Like I'm in the hunt for this magical vector U star. And here comes the connection to Caratheodory. As I said, Y star is a probability vector. Hence, if I look at the columns of my matrix C, so C, note that is an n cross n matrix. So I can just look at each column of my matrix as an n-dimensional vector, draw them out. Then Cy star is a vector that lies in the convex hull of the columns of C. I don't know exactly where this is, but it is in the convex hull of the columns of C, just because Y star is a probability vector. That's the connection to Caratheodory's theorem. So the Ci's represent the n-dimensional columns of C. The vector U star or Cy star that I'm trying to look for is somewhere in the convex hull. Okay, so here's a technical fact, and again, sort of useful and kind of alludes back to why do I need the Caratheodory's theorem for like general P, is the following, that my condition was that C is S sparse. Every column of this matrix C, which is the sum of the two payoff matrices, is S sparse, which means that the log S, and it's normalized, means that if I look at the log Sth norm of every column of C, then that's at most 2. A simple calculation. Like there are only S non-zero entries, the log Sth norm is S to the log S, which is at most 2. This essentially means that modulo this constant, all these columns are vectors that lie on or inside the log Sth unit ball. So I am working with the log Sth norm here. It's very useful to have the approximate version of Caratheodory for general, not just the Euclidean, for general norms. So with this scaling in hand, I have a very good idea, which is, I don't know where this Cy star is, but I can apply approximate Caratheodory to know that there exists a vector that's epsilon close to it in this log Sth norm, which is in fact a convex combination of at most 4 log S over epsilon square VI's. Again, I don't know where this is, but wherever it is in the convex hull, approximate Caratheodory guarantees me that there always exists a nearby vector, which is a convex combination of very few columns of C. Right, and that's it. I'll now do the dumbest thing possible. I'll just exhaustively search for W prime. There's a simple technical fact that I didn't mention, which is that this W prime is in fact a uniform convex combination of a very small number of columns of C. In fact, this W prime will be a convex combination of like 4 times this norm log S by epsilon square columns of C. I just enumerate all n choose log S columns of C. For every candidate W prime, I solve a linear program and test whether I have a Nash equilibria or not. That's it. So in particular, I just, as I said, I just enumerate over all columns of, all small size subsets of columns of C, and this gives me this result. So this n log S, n to the log S essentially comes because I'm looking for all log S over epsilon square size subsets. I'm enumerating over all this size subsets of the n columns of C. That's it. Exhaustive search. For every choice, I solve a LP, and the solution I get, I can test whether it's an approximate Nash or not. This is existence result. It guarantees that at some point or the other, I am going to succeed. That's it. So here's the general point that I never use the structural property of this bilinear program. Give me any quadratic program where the objective matrix is sparse, I can apply the same idea. I did not touch any specific properties of the bilinear program here. As long as the constraints are linear, I can just apply it to any sparse QP or bilinear program, and this sort of naturally gives me a second application, which is finding densest subgraphs. So again, popular problem studied in approximation algorithms. The problem is that you're given a graph and a size parameter. You want to find a subset of size k of the largest density, the largest normalized density, hence the normalized version of the problem. Formally, I mean that the density of a subset is the number of edges in the subset divided by k squared. So I'm normalizing the density to be at most 1. The goal is I'm given a graph G and a size parameter k, want to find such a subgraph, such a subset of vertices that has the highest density. Roughly speaking, I want to find a clique. I want to find a subset of size k that has as many edges inside it as possible. Again, normalizing it, but the point is that you can write this as a quadratic program. Again, use the exact same idea as I mentioned of doing an enumerating over subsets, solving LPs, yada yada yada. What you get is the following result, that if you have a degree d graph, then in time n to the log d, you can find a k densest subgraph, normalized. The point is that why is this log d appearing here? Note that if I look at the adjacency matrix of a graph, the sparsity, the number of non-zero entries in any column, is exactly the degree. That sparsity exactly translates to this degree, and I have these two applications. Out of time, so I'll not talk about the proof of this. It's actually, again, like probabilistic method and some, as I said, Kinchian's inequality, but we'll want to say that you can actually extend this result to convex hulls of matrices and look at matrix norms. For example, here's a approximate version of Birkhoff von Neumann. I mean, you can do much better than this. This is just applying it as is. For Birkhoff von Neumann, you can get 1 over epsilon. And there are some other extensions to what's called the Shapley-Folkman lemma, again, like a Minkowski sum of convex hulls. There's a nice result called the colorful Caratheodory theorem. Talk to me about this offline. You can get approximate versions of this theorem as well using the machinery I mentioned. So I'll stop here. Thank you. Yeah. Yeah, I mean, all you need is the p norm of every column is small. I mean,